All right. Welcome back to the lab. Welcome back to the final part of our series called What Even Is. I've got a sneaking suspicion that this one might go a little faster. I've got a sneaking suspicion that this episode might be a little short, but then again, I can tend to find a way to ramble, so perhaps this one will be just as long as the rest. I don't know. Let's find out. There's only one way to find out, so let's dive in. Today we're going to be putting the icing on the cake. We are going to be finishing our series. Like I said, we've got the PID controller, we've got the air amplifier, we've got the summing amplifier, we've got the MOSFET. And what we're going to do today is we are going to flip this thing on its head. Rather than using this circuit as a current source, we're going to use it as a current sink or a basic electronic load. So, what are we going to do? It's really quite simple. We're jumping right into LT Spice. You might notice there is no longer a load because we are the load. So the way that looks is the voltage source coming in. We added just a tiny little bit of series resistance, and then our electronic load takes up all the circuitry here. For the most part, this all looks about the same. We've got the P term up here, we've got the I term living down here, we've got the D term with the amplifier, just like it should be. Those three terms come in equally weighted, get amplified, and then come out to our MOSFET. You might notice this extra 100 ohm resistor, and the reason why is because what we've added is this clamp circuit here. Basically, we've got a comparator monitoring the output current. We've got this little filter, this 33 picofarad 100 ohm filter, coming in with a 0.3 volt or 30 amp trip threshold. Whenever the output current exceeds 30 amps, this comparator will start to enhance this NPN, which will enhance this PNP. We're using these as current amplifiers because we're responding to pretty fast glitches. I don't want to have to wait for that amplifier to get up to 4 volts, 3 volts to enhance a MOSFET. I want that thing to trigger right away. I want that to trip as soon as it can. So basically, we take the current coming out of that comparator, we amplify it by beta of Q1, amplify it by beta of Q2, and then what we see on the clamp circuit is something that should, in theory, get up to around 10 volts. And basically, we dump a bunch of current into that C6, and then it'll slowly discharge on R22, and that's kind of like our fault retry time that will basically dictate how long it takes for M1 to turn back on. Why? Well, because what that clamp signal is clamping is we clamp the reference input voltage, basically clamp the current set point to 0 amps, and then we clamp the output MOSFET to ground. So we don't wait for any of our PID control loop to respond. We don't wait for any of that. The second we trip over 30 amps, this circuit will clamp down on the gate of that MOSFET, clamp down on the input voltage reference, set our set point to 0, set our output current to 0. And basically, we will respond as fast as we can discharge the Miller capacitance in M1, the gate capacitance. So that's the theory. That's what we're doing. That's what we're going to test today. To show you why we did that, we're going to run 2 main simulation runs. We're going to run a simulation run without that clamp circuit, and one with. To make sure it's disabled, I'm just going to tie that to ground. We're going to hit run. What we're going to see is the input voltage oscillates. So it goes from 0 volts and someone plugs in, they hot plug 200 volts. Or it could be a 200 volt source that turns on. And what do we see? Our current waveform, well, it overshoots a little bit. We're shooting for 10 amps. We hit as high as 50. Now, that could be a problem for more than one reason. You can kind of see the D term start to play its role. The D term helps to compensate as much as it can, but there are some fundamental limits to what we can do here, right? This is a controller, it needs to wait for the iTerm to respond. And during that time, we pass a fair bit of current, right? You can see the sum of the output. We are hanging out at 9 volts, and we need to bring it back down to 5-ish. It's not great. It's not great. However, all things considered, 200 volt input, basically no load, no resistor. That's not a bad fault current. We're limited, I don't think that was limited by our 10 milliohm resistor. What would that be? 200 volts, 10 milliohms? I think that'd be 200. No, that'd be more than 200 amps. Yeah, that'd be lots and lots and lots of amps. That'd be more than 2,000 amps. So this controller's responding very fast. However, I think we can do better. So right now, without our clamp circuit, we're limited to about 50 amps. That's just our PID controller with where we left it tuned in the last video. Let's connect our clamp circuit and let's see what we can limit that over voltage to now. Hey, look at that! Our fault current is limited to about 32 amps. So when we look at that voltage waveform, you can see there's this fault time, there's the initial fault, we trip, comes back on, there's a little bit of a surge, and then we end up right where we should be. And sure enough, yeah, look at that clamp circuit. It gets triggered by that small fault condition, and then the time constant of the resistor discharging the capacitor takes us to where we should be. Excellent. And how does that look on the MOSFET gate? Oh, look at that. Look at that. That is a fast response time. Look at that. So we exceed the current threshold. 30 amps. That is 30 amps. And the current trips at how fast did we respond? Wow! We responded in about 10 microseconds. Now, it would probably take a little longer in real life. I'm sure there's some delays that aren't being modeled here. Propagation delay, so forth. But that's not half bad. For dropping 200 volts on this bus in a time of 0.01 seconds, that's pretty good. That's pretty good. And just to take a look at what our controller is doing. Yeah, it looks like our iTerm is still a little bit high when we come back around. So yeah, that's why we had that little glitch, because the iTerm hadn't completely reset, so the gate voltage was still a little high. Awesome. That's fantastic. I love this. Yeah. So we basically take our reference, we just clamp that right to 0, take the gate, clamp that right to ground, basically turn off our output FET by applying about, well, negative however many volts are across this current shunt, and wait the fault time and then re-enable. That's fantastic. So that's the fault timer that we added. And typically, right, this would be set, in this case it's set 5 amps above our nominal current, so it leaves a little bit of room for that overshoot and ringing, normal conditions. And that actually allows us to reset. We get pretty close to tripping again. But we don't. If we want to make this take a little longer to respond, we can increase C4, we can increase R21. All of those things will allow our circuit to recover a little better. But in general, I'm liking the way that this looks. Just to show off what happens when this isn't a fault condition, I want to change the order of operations here. Because right now, our set point turns on at 1 second. If we change our set point to turn on at 6 seconds, I think we'll get to see something very fun. Let's run that again. So now we're going to see, so we turn on the regulator, commanding 10 amps at 6 seconds. The input voltage increases at 5 seconds. What do we see? So we see a nice controlled turn on event. That's fantastic. That's right where we left the regulator. A little bit of overshoot, less than 1%. Settle out nice and quick, just like we should. And yeah, that's just because of how we've tuned the PID loop. That's behaving exactly how we would expect it to. Then, of course, the regulator, the input voltage turns off at 7 seconds, like it should. We can see the output of our compensator go from its steady state value, where we're regulating to 10 amps, up to the maximum for the system. Yep, we're just hanging out at 9 volts. Then the 200 volt source comes back. Since the MOSFET is enhanced, what we end up doing is we trip the overcurrent threshold, protecting that MOSFET and protecting the upstream load, so there's not like a short or anything. Like, yeah, that's looking fantastic. I love this. And then we end up coming back into regulation with a more aggressive bump. It looks like when we're recovering from a fault, there's a little bit more of a transient. So perhaps our fault timer could use a little bit of work. Maybe we should use like a 555 timer where we can have a more repeatable pulse. Yeah, I would expect the integrator to respond more. Oh, it's because our current was 0 and our set point is 0, so it doesn't actually output a negative error. That's a shame. That's a shame. And the only way to make that output a negative error would be to do some trickery here. Well, there are some ways we could make that happen. So I'll keep that in mind. If we could clamp this to like a negative, anything negative, like negative 0.5 volts, that would be enough, but we just need to be careful that we don't tie it to too negative of a voltage, that it leaves this MOSFET normally enhanced. That would be a problem indeed. So where does that leave us? For those watching at home, you might not understand how critical this little addition was. You might be looking at this and saying, hey, that looks almost the same. And you're right. It does look almost the same, but now it's fault tolerant. Some of you might know how we blew up the electronic load that we got for like $30 on Amazon or eBay or Alibaba or wherever you buy yours. Ours blew up because of a situation like this, where there was an overcurrent fault and there was no hardware protection. There was no hardware fault timer or clamp circuit that would protect the MOSFET in a fault condition like this. So what this will actually do is, let's say, for example, we know the safe operating area of this MOSFET. There's a curve that says for every voltage, how much current that MOSFET can dissipate. Or in other words, what is the peak power that this particular MOSFET can handle? And what we could do is we could have a DAC. We could have a programmable voltage source that is used to set our target voltage. Likewise, we can have a DAC that sets our overcurrent voltage. Or, even better, we could use a DAC and a resistor divider such that our overcurrent voltage is always some percent above the set point, so that we can use one DAC and accomplish both functions. That could be pretty cool. 2 birds, 1 stone, one less component. And the intention here is to have a controller that is running independent of the micro. So we've got a hardware control loop that is always regulating with some kind of interface to the digital world, so that we can either have programmable step currents, or you could give it like a file, like a PWL file, like you can in LT Spice, where you basically end up with a programmable load where the microcontroller could read from an SD card or could receive commands over USB or serial or whatever, where you basically give it points or times or do real-time data transmission and have it live update. There's lots of ways that this could work, and basically you just have an isolation barrier between your communication interfaces and the digital circuitry living in this high voltage region with the plus minus 10 volt stuff. And in theory, as long as you've got some hardware protection for fault conditions, like overvoltage or whatever, like we could basically modify the fault current to always keep our MOSFET within the safe operating area limits. And in theory, we could make an unbreakable electronic load where, in all normal cases, the clamp circuit will protect the MOSFET. In fact, we might be able to use the input voltage as an input to set our fault current automatically. That could be cool. So we just like draw a line of current that's allowable. So we could even program an unsustainable. I might like that. I might like that. Leave it up to hardware 100%. But there's lots of ways that we can make this go. And as we get into the detailed design process for our electronic load project, this is going to be cool. Make sure you stay tuned so you don't miss it. Before we do that, though, I want to take a moment just to show everyone that this fault circuit indeed does not interfere with the normal operation of this design. We're going to do that by dropping one over there, the other one over here, and we're going to hit go. And this is going to be pretty cool because what we're going to see is we're going to see how we are driving a waveform. Oh boy, we're getting stuck with stepping the source. There we go. So you can see the input waveform that we're asking for. We're asking for 25 amps going down to 0.1, back up to 25, back down to 0.1. This is something that we've seen before. But now we're combining that with the input voltage falling away. And what we're left with is something that follows the waveform, except for when you drop 200 volts across it. And when you look at the output of our compensator, that's pretty cool. Like, this is pretty cool. And in order to make this work better, right now, this is just a standard FET because I couldn't find a good model for linear MOSFET. Linear MOSFETs are basically designed for this. They have a much wider safe operating area. They tend to have a much larger gate charge or gate capacitance, but they've got an extended Miller region or Miller plateau, whatever you want to call it. I've heard it called many names. I'm just trying to use them all. But that linear region of the MOSFET is larger. So rather than being on a 10 millivolt operating range for our V gate, might be 100 millivolts or 150 millivolts in that linear region. That will help this system a lot. Yes, indeed. I'm very excited about this. There's a lot of nuances that we're going to need to cover, like making sure we're going to be stable with that much gate capacitance hanging off on the final amplifier, making sure we've got good transient response, oh, it's going to be good. It's going to be good. There's going to be a lot of good engineering design that's going to go into our electronic load. I'm hoping that we can get some high precision. I want some high accuracy electronics going on. I want to get precision current source going. I think that's all we got for today. How'd we do? Yeah, I think it was a little shorter. So, this is going to be the fundamental structure. There's a lot of nuances not considered. Maybe we'll need the D term. Maybe we won't. Maybe we'll stick with PI control. Maybe we'll build a type 2 compensator instead. Maybe we'll make it so that there's a bunch of DACs or analog devices or digital potentiometers that are allowing us to tweak some of our coefficients on the fly if we need that. Maybe we can find some coefficients that'll work in general. It's going to be an exciting time no matter where this project ends up. I cannot wait. If you like this video and you can't wait for more, don't forget to hit that like button, get subscribed, or check out the links in the description of this video. What you'll find down there is this simulation file and also links where you can follow us on Patreon or support us there, get in our Slack channel. There's lots of ways to get connected with EEforEveryone. All right. This is all we've got for the What Even Is series. Thank you so much for watching. If this is the first video you've seen in that series, don't forget to check out our playlist. It's pretty sweet. Yes. But most of all, I hope you learned something great today, and I hope to see you again soon. Thank you so much for watching EEforEveryone. I hope to see you again soon. Bye.